Okay, now I'm going to import this file into Fluent. So open Fluent from Start menu and choose Solution, 2D, Double Precision and 4 cores, and select the working directory by browsing from here, and then click on the mesh. So the mesh file is cylinder course.msh, and then click on Start with selected options. Okay, we are getting some error in the mesh. So I will go back to the ICM CFD, and I found that the error is because of the boundary conditions for the fluid region. So it should not be interior. We can create, let's say, if we make it fluid, so what will happen? Okay, so again convert to unstructured mesh and export the mesh. Okay, this time I will not provide any name here, so until we get the solution. So 2D and done. So default name will be used, which is the fluent.msh. Okay, now we don't face any problem. So either delete that boundary condition completely or make it as a fluid, not the interior. Okay, you can delete this one also, and but default name will be selected in the ICM CFD, and same name will be transferred to the Fluent. Okay, so now we have the mesh file with us, and this is the with the problem mesh. Only problem was that we defined the wrong boundary condition type for the fluid region, so it should not be interior. Okay, now if we display the mesh, it's the mesh file with us. It's a very fine mesh near to the surface. So I'm thinking to do one thing, that if I go here and if I change the first cell height to some other value, for example, if I make the first cell height to 10 power minus 3, okay, and let's see the mesh. Or we can make it 0.005. Right click on the pre-mesh and check mesh, recompute. So you can see we have the more cells over here. So I think this mesh will be okay. So I will be copying meshing parameters from the inside to the outside of the blocks, the neighboring blocks. And this should give us the more decent mesh. And similarly over, not here but here, and also here, and right click on the pre-mesh and recompute. So this is more refined mesh, and I can put the more cells here, like maybe I can put 40 cells. Okay, and copy the parameters from this edge to this edge here, and we can make it geometric one, for example, and apply, and I can put more cells, like maybe 30. So now we have the more refined mesh in the back region. Okay, and the difference of the number of cells is around 22,000. So convert them into unstructured mesh and don't make any other change in the mesh. Simple. So directly go to output mesh and from here export the mesh from here. So this is 2D and cylinder course. Okay, so you have to reread the mesh file. Mesh type is the simple MSH and cylinder course. Okay, you can also change the color by some surface, and you can also change the color of the interior. This is now known as the interior inside the fluid. So you can change the color to light blue, light gray also, and maybe you can choose the magenta. So you can have the many colors. Okay. Now we have to, first of all, we have to choose a laminar flow model. So laminar from the viscous SSTK omega. Click on OK. In the material properties, we have to provide the density, which is a 1, and the viscosity is 0.006667. So once again confirm, this is 0.006667. Okay, close. And in the boundary condition, I'm going to put the boundary condition for the velocity inlet as 1 meter per second. Apply and OK. In the methods, I'm going to choose a coupled second order scheme for every variable. It's so okay. I will come back here, and also from the journal, you have to make it transient. Okay. Again, go back to methods, and here you can see now we have the transient formulation as the first order. So make it second order. That's all. In the controls, choose the default settings for the under-relaxation factors, and in the report definition I'm going to make the few monitors. So first of all, I'm going to make the few points, and the locations of the points I know. So location is given here. Okay, the first point is point number 1. This point is at the x is equal to 1 and y is equal to 0.5. So create. And the point number 2 is at the x is equal to 1 and y is equal to 0.75. Create. And the point number 3 is at x is equal to 2 and y is equal to 0.5. And point number 4 is at x is equal to 2 and y is equal to 0. Okay, so if you take a look on the mesh file and don't display the interior of the mesh, so you will see these 4 points. We should be having the 4 points. So fourth point, point number 1, 2. Okay, so point. Okay, so let's delete these points again. So these points have not proper names. Okay, so the first point, point number 1 is at point number 1. So it's the x1 and the y is equal to 0.5. Okay, and the point number 2 is at the x is equal to 1 and y is equal to 0.75. And the point number 3 is at the x is equal to 2 and the y is equal to 0.5. And the point number 4 is at the x is equal to 2 and the y is equal to 0. Okay, so these 4 points are here. One, two, three, 4. Okay. Point number 1 is here, point number 2 is there, point number 3 and point number 4. Okay, alright, so now I'm going to make the report definitions, and here right click on and new. So this is going to be force report, and lift and also drag. So this is the lift coefficient, and we have to provide the reference conditions also. So in the reference condition, the density, take it from inlet. So area is the 1 because the diameter is equal to 1. So 1 into 1 is equal to 1 meter square. Length also equal to 1. Depth is a 1. Temperature is 288.16. Velocity is 1 meter per second. That's all. And now lift coefficient on the cylinder. And this is going to be along the y-axis. And this is the lift coefficient. Okay, print to console also, and okay. And the second definition is about the drag coefficient. Drag coefficient. Okay, this is along the x-axis, and print to console also, and okay. So you will see that we have these monitors. Okay, and also for residuals, make it 10 power minus 20. So 1 e power minus 20, and copy them to all the fields, and okay. And then we have to make the few more rapport definitions. So it's a surface rapport and vertex average, and it's a velocity, y velocity, and point number 1. So point 1 monitor. Okay. Okay, similarly you have to do these things for the remaining 3 points. So this is for the last point. Okay, now I will initialize solution first using some method. Any method can be here. So use hybrid initialization. Okay, next thing is that I will go to the domain, and from here we have the adopt option. Adopt means that you can adopt the mesh and define the mesh locally. So I'll use for some other purpose. So I will use a manual option, and it's a cell register, and I will be using the boundary. Not the boundary but region. Okay, and this region is along the x is equal to minus 20, and x maximum is the 45, and y minimum is 0, y maximum is the 20. So this is a 1/2 of the domain. So 1/2 of domain is from here to the top. Okay, so this is register number 0. So click on save display. This half is on the upper side of the circular cylinder. Okay, then put the name as a region number 1, which is going to be the bottom part. So only change is that you have to make minus 20 here. Okay, so now we have the 2 regions, and display option, if you go here you can draw the mesh, everything you can draw. Okay, so you can now close this panel, and now again go back to the solution initialization and click on the page. So basically what I'm trying to do is that you know that the water shedding is basically the disturbance in the flow. Simple thing. The water shedding is the fluctuations in your average flow field. So that is behaving in this way. So some velocity is going down, then some velocity is going up. So if you provide disturbance by yourself in the initial field, so the convergence to the transient flow will be faster. The flow will accelerate to reach to the its unsteady region very quickly if you provide some unbalanced flow field. If you provide unbalanced flow field, the flow will quickly develop these water shedding very easily. So that's why I'm going to provide the flow field that is disturbed one. So in the region number 0, I will provide the x velocity as the 0.5. Okay, so 0.5 and pitch. And in the bottom part, I'm going to provide the velocity value as the minus 0.5 and pitch. Close, and if you go to results and from the contour plots, if you display the velocity field, you will see this thing. So you can see that x velocity is minus 0.5 on the bottom side and plus 0.5 on the top side, and then there is a mix of the two velocities here. This is basically is an imbalanced flow in the directly into the flow field. This will initialize the disturbance in the flow. That's what we need. Okay, and now the run calculation, and before that you have to save the solution animation. So right click on the solution animation and new, and this should be every time step and new object, and this is going to be the vorticity magnitude, and I will be making the range manually. So this is from 0 to 1 and on the screen. Okay, and then from here we have to, I think we should be selecting the contour number 2 and go to manage views, and I will be making views in this way. So I want to save this view. So once I save this view, I can, if I move this thing anywhere, and if I click on the view and apply, this view will be brought up on the screen. Okay, so I will choose this view for my animation and click on OK, and make the animation number, let's say this is the animation for vortex shedding. Okay, click on OK, and number of time steps, let's say we provide the many time steps, and time step size, I told you that this is equal to the how much value? We're going to use the 40 time steps. So for 40 time steps in a one cycle, this means that we have to use the time step size of 0.1453. Okay, 0.1453. Now click on calculate. And you can observe that the disturbance is being converted into the vortex shedding, and on these plots, they will be quickly turned into the transient behavior very, very quickly. You can also observe this thing over here. And now you can notice that the vortex are being formed, and so after certain time steps you will see the vortex shedding will be there. And as you can see that if you take a look on the CL, this is also periodically converged, and this is around after 50 seconds flow time. And same goes with the drag coefficient, but drag coefficient, because the scale was very large, so that's why you cannot see the fluctuations in the drag coefficient. But if you take a look on the velocity profiles, you can clearly see that we have the fluctuations in the velocities at different points, and they are periodic around 50 time flow time. So now this is time to stop solution, and the next thing is that we have to stop solution here right now. Okay, so the animation is completed, so I can export the animation from here right now. And at the same time, you can save the file also. Okay, so now from the playback, so we have the around 895 or 900 frames, and make the video file, and this will be in the your working folder, which is we created in the E drive. So you can create anywhere, and then click on write. So this will also write the animation file, and also it will show you on the screen. If you look at the Fluent window, you can see that the animation file has been written on the hard disk, and this is the animation file. And from here you can clearly see how the flow is developing and changing into the vortex state, von Neumann vortex state. So unwanted effects are going out from domain, and then the flow is stabilized only for the vortex state. So it is around half of time. After half of time, the vortex state is fully functional, and you can see the vortices are being formed there, and they are being convected downstream. Okay, so now we have to adjust few more things here. Number one is that we made the animation, that's all. So now I can remove the animation file from here. Very simple. So we don't need to waste our resources on these files. Okay, and also there are some frame files that you can delete to save your space on hard disks. So these all files are the frame files which are used to save the every frame for every time step, and then they are used to make the animation from these all picture frames. Okay, so you can delete them simply. Okay, next thing is that we have to delete these all monitors from here, and then we have to create the new monitors, because here we have some initial transients also into data, and if you every data for with these transient initial change in the values, this will make the data polluted. So we don't want this thing. So that's why we are going to make the new reports here. So new force report, drag coefficient. So we just need two things, drag coefficient and lift coefficient. Okay, so drag coefficient for getting the average drag coefficient, and lift monitor for fast Fourier transform to get the dominant frequency, and from dominant frequency we can get the value of the Straub number. Okay, simple thing. So just two monitors are needed here, the lift and the drag. So lift coefficient, this is the lift coefficient. Okay, and click on OK. And since we are simulating the 40 time steps in a one cycle for time step of size 0.1453, so I'm going to simulate this case for 10 time steps, 10 cycles. So 10 cycles. So 10 cycles means the 400 time step should be there. So for the last simulation setup, I'm going to simulate the 400 time steps, and that is roughly equivalent to 8,000 iterations. Okay. So now we will observe this data for the next 10 cycles, that is equal to the 400 time steps. Okay. And now click on calculate again. Okay, you can stop and you can delete these monitors from here. Okay, one more thing, if you compare the monitors, you can see the monitors given here, they started from a straight line because we initialized with a uniform value. So initially the flow was stable, and once the disturbance was observed by the flow, then it changed to the periodic behavior. So it took long time. But if you provide the initial disturbance by yourself, the flow can quickly move to the transient phase very, very quickly. So anyhow, so now click on calculate. And now you can see the drag coefficient, lift coefficient very clearly. Okay, so this is the idea of this video, that we have to set up the problem and then how to observe data, how to make animation, and then finally we have to run the case for the final cycles for which we have to analyze the data. So in the next video, I will show you that how to average out the data, how to apply the FFT, fast Fourier transform, get the average value of the drag coefficient, get the root mean square value of lift coefficient, and then also get the frequency, and from frequency get stall number.